Okay, so we've given a definition of the integral. This is called the definite integral, actually. So I should say it's the definite integral. And this sum right here has a name. This sum is called the Riemann Sum, after the German Riemann Sum. German mathematician Riemann. Good. All right. So one way to talk about the definite integral then is it's the limit as n goes to infinity of the Riemann sum. Good. All right. So just to talk about the notation a little bit. So the integral sign is actually an elongated S. Kind of comes from the old English, I guess, is the style. The A and the B are called the bounds, and so A is called the lower bound, and B is called the upper bound. Remember that A and B define the interval on which the function is going to be. And on let me draw a picture instead of trying to talk. If this is my function, notice I'm making my function all positive right now, and that's A and that's B. Then the integral is going to represent the area under the curve from A to B. So the definite integral represents the area. Good. And so f of x, by the way, is called the integrand. The integrand. Can I spell that better? Okay, and then a lot of people get a little bit sloppy and don't include dx. Please don't do that. You got to include your dx term. This tells you what the variable is, or what the independent variable is, I should say. Because sometimes you'll have some other constants floating around in there, and so it's not going to be always clear what the independent variable should be. Okay, so again, f of x is called your integrand. Dx is actually your little differential, but it tells you what the independent variable is. The upper and lower bounds are b and a, and the integral sign is like an extended s. So just for practice, that's the integral sign, integral sign, integral sign. Okay, good. I should just mention Theorem 3 in the book. We're not going to delve into that very much, but if f is continuous on the interval from a to b, or if f has only a finite number of discontinuities, I don't want to say that. Gosh darn it. The discontinuities have to be a special type of discontinuity. They have to be jump discontinuities. Jump discontinuities. Then the integral will exist. Another way to say that is that f is integrable. Okay, and so what do I mean by jump discontinuities? This would be an example of a jump discontinuity where the limit comes as you come in from the left and the right exist, but there may be a discontinuity right at one single point. Versus this kind of a discontinuity, this is where we have to be careful when we're finding area under a curve, because our function doesn't have a nice shape there. And so not a jump discontinuity. So we're not allowing that in Theorem 3. Okay, this is a jump discontinuity. Okay, so typically we're going to assume basically that our functions are always continuous and then just leave it at that. All right. We're going to deal with discontinuities in the integral at a later time. Okay, so let's just take a look at a few examples here, just to get used to the notation. What is the integral from a to b of the function c? Here's a hint. How about if we draw a picture? Yeah, what is the integral going to be in that? Well, I guess I'm going to draw it that way. Good. The area then is going to be the integral is going to be the area of that rectangle. What's the area of the rectangle? C times b minus a. Good. So this is kind of our first property. If I want to integrate a constant, I get a constant times b minus a. Or it's the height times the length of the interval. How would I do something like the integral from 0 to 1 of the square root of 1 minus x squared? Well, you might recognize this from before. What does the square root of 1 minus x squared look like? It's the upper half of a circle. And so if we're just going from 0 to 1, that actually means that it's only the quarter circle. And so then by geometry then, we know that this is the area of a quarter circle. And so that's going to be pi r squared divided by 4, where our r in this case is 1, so we can just say pi fourths. Pi fourths going to look a little weird there. Pi fourths is what I'm trying to write. There we go. Very good. All right. How about another example? So this is kind of getting at the idea that you don't always have to use the Riemann sum, right, to find the area. If you can use geometry, it's a good idea to use it. 0 to 3, x minus 1 dx. Now, I'm going to use geometry to do this one too, but it would be a good idea to sketch the graph of this because it's going to look something like that from 0 to 3, where this is equal to 1 there, right? That's 3. So that's 3 minus 1 is 2, so this height right here is 2. All right. So what is the area from 0 to 3 of x minus 1 dx? Well, remember what we were talking about before when the bug was crawling around on the wire? The negative area actually corresponds to, you can have a negative area, right? We would have to give it meaning, like negative area might be to the left and then positive is to the right. Or we might say that negative area is down and positive area is up. So that's kind of giving us a direction. And so in this case, our area is actually negative here. So that's going to be minus 1 by 1. And then here it's going to be 2 by 2, right? And so the actual area here is going to be the positive area minus the negative area. Or I shouldn't say minus the negative. It's going to be minus the area under the line, under the x-axis. So that's going to be 1/2 the big triangle here. It's going to be 1/2 2 times 2 minus 1/2 times 1 times 1. Good. So that's what I mean. 4 over 2 is 2 minus 1/2 is 3/2. Good. And so what I'm trying to get at, but I'm not really doing a good job at it, is that the integral from a to b f of x dx is the net area above the x-axis. Okay. So that's different than the area under the curve, right? If f is positive, then we could say that the integral is the area under the curve. Okay, but you have to be careful about that negative area. So if you're not sure, you could compute the absolute value, the integral of the absolute value of f of x, and that would be the area, the actual area between the curve and the x-axis, right? Because just as a quick example, if the original function was this function, right, then what does the absolute value of the function look like? I'm going to flip this around and then go up. So the purple curve is the absolute value function, and so if I take the integral of the absolute value of f of x, I get the purple, right? And so that's going to be the actual area between the x-axis and the curve. Good. So in a similar way, we were talking about position being position was obtained from velocity in much the same way finding the area under the curve. But we're going to get to that again later. What I wanted to mention, though, is that for velocity, v of t, we just want to recall that speed is the absolute value of velocity. Good. All right. So we're going to talk about the physics a little bit more later. Okay, so in the next video, we're just going to talk about some properties of the integral, and they'll be fairly straightforward, but we should list them all just so we know what the properties are that we're using. Okay, see you then.